Hey folks, today we're going to talk about resistive force on a moving bar in a magnetic field. Now before we do that, in the previous video, either in class or the video that you watched, you learned that the voltage, which is otherwise known as EMF, of a bar moving through a magnetic field is equal to BLV. B magnetic field strength, L length of the bar, V velocity of the bar. The way that was done in that video was they looked at the force on a charge. So for instance, if you're a little positive charge in here, you do your right hand rule, you're moving to the right, you're in a field that points into the page, you're going to be forced up. So you'll end up with a lot of positive charge there and a lot of negative charge there. Okay, this would be the higher voltage. And then, of course, the bottom would be the lower voltage where the negatives are. Okay. Now, there's a second way to derive the equation that they got, and I do want to mention that. So let's say you were to put this little bar on some metal rails, okay, like so. And this now makes an area, this area right here. And we'll call the width of that area, we'll call it W. And then the length of the area, this length of the bar, we'll call that L. So another way to get this BLV is to say, okay, I'm going to use Faraday's law. So EMF is negative d magnetic flux dt, which is negative the derivative of B times A times cosine of theta, which isn't changing, so don't worry about that. All right, so you got this, right? So this equals the negative derivative of B times the length times the width. Okay, so which of those three things is changing as the bar moves to the right? The magnetic field, the length, or the width of your rectangle? Well, it's the width. So what you end up with is negative BL, and you get dW dt. Well, what's dW dt? That's the speed of the bar. So that's another way to get negative BLV. Okay. Now, by the way, there's a negative sitting there that wasn't in the previous video. The negative has to do with the direction. We'll talk more about that. That's Lenz's law. Okay, so we've either already talked about that, I think we've already talked about that, or we're going to talk about that. That just has to do with the direction of the moving charge. Now, something else that's really important here. This is going to come in the next several things we do. Current's going to flow. Okay, if you put this bar on this metal rectangle, okay, current's going to flow around the rectangle. So first of all, which way is it going to flow? Well, it's going to go, current will flow from the high voltage to the low. So in this case, in this circuit, your current would go counterclockwise. Okay, so it's going to flow off the top of the bar around your circuit to the bottom of the bar. Again, we're talking about positive conventional current here. Now, when that current flows, that current experiences a force, which is equal to ILB. Okay, that's from our previous chapters. Now, force is equal to I, which is going to be the voltage over the resistance times L times B. And we have an equation for that voltage right there, right? That's a negative BLV. So the force will equal negative BL velocity over resistance, okay, times L times B. And if you put your like terms together, you get negative B squared, L squared, velocity over resistance, okay? So that is the resistive force acting on this bar. In other words, if you try to pull this bar to the right, there's going to be a resistive force to the left that's going to try to stop the bar from moving, okay? So that's going to come into play in many of the next examples. We're going to talk about the motion of different conductors under different circumstances. So you definitely need to know that this is resistive force. So I can write that down here. And you're going to use it a lot in the next bunch of stuff we're going to do. So again, a second way to calculate this voltage of a moving bar through a magnetic field, VLV. And when a conductor is moving through a magnetic field and current is allowed to flow, you get a resistive force, and it's equal to this crazy thing here, V squared L squared velocity over resistance. All right, hope that video was helpful, and see you in the next one.